Hello and welcome back to Calculus1 on this wonderful Monday morning. It is sunny, 73 degrees with a nice north breeze. No? I thought I'd give you a weather report along with this. Would be helpful. Optimization problems. We are going to work on the word problems that are very useful and applied, obviously. This is going to be application of 4.1 min and a max. So optimization problems are after trying to figure out minimum, maximum, and all that. You want to know maximum profit, minimum cost, maximum area, minimum volume, or things like that, for various types of applications. But first, let's talk about the concept. So we're going to work on a problem that has zero application. It just illustrates the way to do all of these problems. So it's going to be the same, very structured like your related rates. And you just have to be careful with geometry, I guess. So we start with the idea, sum of two numbers is to be, let's say, 18. Find the numbers such that their product is max. See, they are giving you a constraint, because if I ask you, give me two numbers that add to 18, you're just going to say, okay, 16 plus 2. And you're done, right? But is the product of those two maximum? The question, right? See, if you just guess 16 plus 2 is equal to 18, I will go and say 16 times 2 is 32. And then ask you, can we do better? And you say, well, I don't know, but I also know that 15 plus 3 gives you 18. And I say, that's better, because 15 times 3 is 45. That's clearly better, right? And then you say, keep going. 14 plus 4 gives you 18. Sure, 14 times 4 is exactly better, right? Keep going. 13 plus 5 is 18. Okay, 13 times 5 is? Anyone? Very good. All right. Keep going. 12 plus 6 is 18. Sure, 12 times 6 is nice. See that? Well, 11 plus 7. This is going to fail, right? No, it actually gives you 77. It's even better. All right, 10 times 8. Because that's also 18. 80. 9 plus 9 is 18. Well, 9 times 9 is 81. Better, right? All right, next one. 8 plus the... Oh. Nice. We don't even have to study this section. You can just guess it. The problem is when it works out that it's some kind of cube root on a fifth decimal, right? Then it's a little bit tougher to guess. But yeah, this is what we were doing, right? We have a constraint that numbers have to add to 18, and we want maximum product of those two numbers. The product is just multiplying them. So you know what? Let me mainstream this, because I'm lazy to do these charts every time. The column on the left tells me that two numbers need to add to 18, right? So this is add to 18. And the other column on the other side, the calculation, says that their product needs to be max. Well, that's simple. right? What we want. You will always have these two equations. The one up on top is called constraint, and the one on the bottom is objective. What do you want to achieve? I want to find maximum product. Okay, that's your objective, right? Your goal. So they're called objective equation and constraint. Constraint and objective equation will be back in Calculus 3 when you do your Lagrange multipliers. So, which is the same thing except in 3D. More equations and more fun, right? So over here, as you can see, what do I have? I have a system of equations. System of equations. Can't solve it because one of the numbers is a max, and I don't know what that number is, right? But what I can do is what is done for every problem. Solve constraint for one of the variables and plug it into the objective equation. This is it. So, where is the hustle in this problem? The hustle is for you to translate the words into equations. The rest is a joke. I'm going to solve the top equation. Y equals 18 minus x. I'm going to plug that into the second equation. So equation 1 solved, equation number 2 plug in. What I have now is 18x minus x squared equals to a max. We know that this max is going to work out to be 81. We figured it out, right? Long way. So we know that this max is a number. What do you do if you want to find a max for a function? How do you do it in 4.1? Come on. What was the procedure in 4.1 to find the max? Where do min and max occur? At critical points. How do you find critical points? And set it equal to 0. Great. So look. As soon as you take this derivative now, you see that this max is going to be 0? Because that was 81, right? We don't know it's 81, but we know it's 81. It could be anything else, right? For different problems, it's going to be a different value, but that's a constant. And when you take the derivative of that constant, it becomes 0. So we're not technically setting it equal to 0, we're just getting that it's equal to 0. So 18 minus 2x equals to 0. When you differentiate, x is 9, y is 18 minus 9, also 9. Numbers are 9 and 9. Now this is going to be the same procedure for every single problem. You will come up with two equations, plug one equation into another, plug constraint into objective equation, and then differentiate objective. That will give you one variable, go back into substitution equation and calculate the other. No problem. So let's talk about very popular farmer problems. So what do you do? Farmer has, let's say, 2,000 feet or 2,000 yards of fence. He wants to fence off a rectangular area of maximum area. I don't know how to say this differently. He wants to, rectangular plot. There we go, rectangular plot. I can do that. So he wants to fence off a rectangular plot of maximum area. Find the dimensions. Of the plot. So farmer has a lot of land, farmer has a lot of fence. He wants to fence off rectangular area so that area is the maximum possible. He wants to use all of the fence. He has 2,000. So what would be the two equations? Anyone? You confused two concepts in one. I'm sorry? 2x plus 2y equals 2,000. Nice. Fence is going to go on the perimeter of the plot, right? That's the pink is the fence. It's called perimeter fence, right? Because it goes around the perimeter, and perimeter for rectangle is 2 x's and 2 y's. You have x, x, y, and y. So 2 x's and 2 y's all around. That's going to be the perimeter of the rectangle. So this is our constraint. And now I need maximum area. What's the area of the rectangle? X times y. We want that to be max. So now we can simplify the top equation divided by 2 everywhere. So we have x plus y equals to 2,000. No, to 1,000. And then we have xy equals a max. The top equation is the constraint. And the bottom equation is the objective. Solve the constraint for one of the variables. So y equals 1,000 minus x. And then plug into the objective equation. So we have x times 1,000 minus x is equal to a max. And you see that this is the same problem like the one with numbers. Right? Over there I said two numbers should add to 18 and the product should be maximum. Well, yeah. Over here I'm adding two numbers. Once I cancel, I'm adding two numbers to 1,000 with the maximum product, with maximum area. So we have 1,000x minus x squared equal a max. We hit this with a derivative to maximize it. we get 1000 minus 2x equals 0, because derivative of that max area is going to be some number. We don't know what, but it's going to be some number. And when you take the derivative of some number, you get 0. So x is 500. Well, then y is 500 too. So plot should be 500 by 500 yard. So if he has 2,000 yard of fence, he can fence off 500 by 500 yards. Great. Let's modify the same problem. Say that this farm, that the land is adjacent to the river, or is adjacent to some other already fenced off area, right? To a nuclear facility or something, right? That's where you put nuclear plants, right? In the states where no one lives and we just have corn, so we can eat radioactive corn, right? Yeah, we need fusion, guys. Anyway. So, okay, let's be less grim. Let's put the river. So this over here is clearly a river, right? It's a stream. You can put some salmon in it. Here. Looks like carrots, but it's salmon. It's just your eyes are terrible. And we're going to fence off a rectangular plot again. We still have 2,000 yard of fence. Looking for the... That's not fence. That's fence. And we're still looking for maximum area. By the way, the fish is huge. It's like whales. That's okay. More meat. Anyway. So now what we have is a rectangular plot that only requires 3 sides. Right? This plot is, you know, let's say for pasture, like animals to graze. Right? They're not going to go to the river. Right? They're going to stay on land. People go to the river, and then they get flesh-eating bacteria. Have to go to the doctor. Animals won't do that. They know better. Anyway, so now what are my equations? Yes, x plus 2y, very good. So now perimeter fence has a different equation because we don't have one of the x's anymore, right? And we still have xy to be max because it's still a rectangle and you still need to figure this thing out. So let's go. You can now solve for x. 2,000 minus 2y. You can solve for any variable. It doesn't matter. Plug that in. We get 2,000 minus 2y times y to be a max. And then hit it now with the y derivative. Oh, don't hit it with the derivative. I have to simplify. Postpone hitting. 2,000y minus 2y squared equals a max. There we go. And now, d dy. Nice. So this is 2,000 minus 4y squared equals 0. Again, derivative of max is 0. And then I have, not squared, just 4y. There we go. From where y is equal to 500. Yard. But now what happens with the x? X is 2,000 minus 2 times 500. is 1,000. So now, plot should be (1,000 by 500 yards) to use all the fence. So what is different now? See, over here we had 2 x's. Over here we only have 1 x. Clearly it's going to give us a different answer, right? Let's spice up further. How about if I want to put compartments inside, like this? So I can put cabbage, rabbits, and tigers. They have to be separated, right? Can't put cabbage and rabbits together. What's going to happen to cabbage? It's going to get eaten, right? And I want my salad, so can't put rabbits and tigers together either, right? I mean, even if you put them next to each other, I think rabbits are going to hang out right here, like all of them, in this area. Next to let me put the color, right there, all of them. And tigers are probably going to hang out right here. Cabbage is going to be everywhere because cabbage can't really move. It's, whatever the roots are, that's what the cabbage is. That's. If cabbage could move away from rabbits, it would, but it can't. That's why rabbits are better than cabbage. All right, glad we cleared that up. So now when you understand that you need these 3 compartments to separate all of these things, right? And you can't put cabbage and tigers together because tigers are going to pee all over the cabbage. So that's bad as well, right? So everything's separate. So now we have the same situation. So what is the calculation now? Well, clearly I have x and another x on top, and I have a y. Yeah, I have 4 y's. Very good. I have 4 y's now because these are fence as well inside, right? Because I need to put a fence between cabbage and rabbits. So now I have 2,000 yard of fence, and we want maximum area. I mean, you want these animals to go free, right? And cabbage to have enough room to spread. I mean, still they're all going to hang out, right, at the edge, but that's okay. You did all you could, right? So what do you have? You have 2,000. Oh, I just came up with a crazy design. You can actually put like this. And put the cabbage here, rabbits here, and tigers on the outside. Then everyone will be terrified at all times. All right. Wow, that's actually, that's a problem. This is a bad design because in order to get to the cabbage, you see, no matter which way you go, you have to go through tigers. Unless you airdrop. Right? All right, fine.
You have to still go past the tigers unless you get like UFO pickup or something.
You can do it with a helicopter. You don't have to go immediately to UFOs. I mean, helicopter will do just fine. There's a line. You've seen those. You've seen them. They help those fishermen, right? And the deadliest catch. right? They have the cord and they lower a person, and then that person picks up another person. Well, this person can actually pick up the cabbage instead. It's a military operation to extract the cabbage from the farmer. Nice. All right. So thank you. That design would not work without really high tech. I mean, you can make those overarching, like in Jurassic Park. You know, they have those walkways to go over tigers. That would work until something goes wrong, and then you can make a movie. All right, good. So it's just the same. We have 2 x's, just count, and then 4 y's, and that has to account for 2,000, the fence, and then you still xy needs to be a max, because you want the maximum area. And then work goes here. And answer goes here. Next problem. Here. What does that mean? Just do it. Exactly. You can have any configuration you want, guys. Here, do this. It's fun. You have your x, you have your y, and then you have your x over 2, let's say, and your y over 2. So now you have 2x plus 2y plus a half of x plus a half of y is equal to 2,000, and then xy equal a max. You can remove the one on the top and put the river there. In that case, you kill these 2. Just combinations are endless. You can put any geometry, as long as you account for every black line that I draw is a fence, and it has to have length to it, and that length has to be accounted in constraint equation, because it's the fence that we have to use out of those 2,000. It doesn't matter what kind of geometry you pick, it's going to be right. Now you can also be very creative and have a circular fence, a triangle, right? Or a trapezoid. Good luck with that one, right? You can put anything, right? Because we don't do fencing only in the square states, right? We can do fencing here as well. So. All right, enough of the farmer. Let's take a look at some shipping regulations, right? Does anyone have aspiration to grow up and work for Amazon? No? That's strange. I mean, they're very powerful. No? Still nothing? I mean, I understand if I said UPS or FedEx or Postal Services, then yeah, fine. Amazon, they have a space. They have so much money. They started a space program. Can you even comprehend how much money they have? It's like, okay, what do I do with all this cash? Well, I can burn it, but that's, I guess, federal regulations, I guess. So how about we start a space program? We did everything else. So let's take a look at shipping. So when you are shipping something, you have to be careful of I'm trying to find the problem here and I can't find it now. You have to be careful with the dimensions. Also, if you're traveling as the airplane, right, they give you the dimensions of the luggage, right, that can fit in the overhead department and stuff like that. So I can't find the exact problem that I want, but we can work on it. So what the most important part of any container that you make, and there's actually a whole engineering branch that actually has a lot of job potential. It's called packaging engineering. You are creating boxes and packaging and containers and things like that, right? And you're also creating, part of that would be also to design not just the case, but actually the box, the enclosure for devices. It's not just, oh, I'm making a cardboard box, yay, right? Well, that too, because it needs to be shipped from Malaysia or whatever, but right across the world in one piece. So it's an important branch. And apparently what I'm hearing from my colleagues is that you get hired out of that major before you even graduate. So we actually started a program here at RV to have a good transfer into those, because the field is really apparently very, very hot now. I don't know, I'm not a packaging engineer. I can be, because that's this. So for shipping, what do we have? It says, well, what I'm interested in, guys, is to make a box that is going to have the smallest surface area possible for the required volume. See, volume is the space inside the box. So let's say I'm shipping ping pong balls, right? If I'm shipping ping pong balls, right, each one of those, or tennis balls or whatever, it doesn't matter. Ping pong balls are fine, they're small. So you can fit a lot of those in a box. So I know how much volume-wise, I know how much ping pong balls take in terms of, so let's say I need a certain volume. What I want to do is I want to minimize the size of the box. Now, why do I want to minimize size of the box? Why would that be important? I'm sorry? Oh, we can fit and ship more, yeah, but there is something about the design of the box, right? So I'm going to put my volume, which is what I need, right, in a constraint equation. But then I'm making objective function to minimize the surface area of the box, which actually minimizes the size of the box. Now, why would I want to do that?
Because the bigger the box, the less you can ship. Like, if the box is smaller, the price is down. And like you said, you can get more boxes.
It does have to do a lot with price. So, yeah, you can fit more on a truck and so on. Material, the box. It's not free, right? Are you selling the box? No, right? That's a clear cost to your business. You have to ship those ping pong balls from wherever you produce them, right? Across the world here. They have to come in, not crushed, right? And you are not selling the box they came in. So that's your cost. By minimizing the surface area of the box, you are minimizing the amount of material used to make the box. And you'll go into your head, well, yeah, what am I shaving off 50 cents? Yes, 50 cents on 10,000 boxes, on 50,000 boxes, on 100,000 boxes. Go figure out what your cost is when you save 50 cents for 100,000, right? So figure that out, right? There's a lot of savings in trying to shave off whatever you can when you're making 100,000 of something, right? So our job is to of all boxes with a square base and a volume of 100 meters cubed. Okay. I'm just trying to figure out. It's a big box, yeah. It's like a shipping crate, one of those. All right, so let's take a look. So this is problem 15. Not exactly the problem I wanted to do, but it's something. So they tell us that the volume is 100 meters cubed. They want box with square base. Trust me, you want the square base there, otherwise it's Calc 3 problem. If it's not a square base, how many variables do you have for a box? 3, x, y, and z, right? But if you're square base, then your x and y are the same. So then you have just x and y. I mean x and z, but call it that way. So I'm going to have a box over here. This terrible box. And Mary is looking, so I have to make sure this is. Are we cool? Okay, thank you. So we have x, and a y. This is a square base, guys. And for this square base, I'm going to actually draw a diagram of what it looks like when I break that box apart. And we can see x's inside and y's on the shorter side. So what are my equations now? Well, the volume is area of the base times the height. So that should not be, right, strange to see x squared y. And we know that we want that to be 100, and that's our constraint. Now, objective says surface area to be minimum. What is my surface area for the box?
The area for each of the sides.
Thank you. Area of each of the sides. So what are the, how many sides do I have?
6 times x.
Top and bottom are the same, and all the sides are the same. So what's the area of the bottom or the top of the box? Yes. So surface area is going to be x squared on the bottom plus x squared on the top plus 4 sides. So 2x squared plus 4xy. So I have my equations. X squared y is 100, and 2x squared plus 4xy equals to minimum. I expect you to be able to compute this now. I already did 3 or 4 of these. Solve the top one, y equals everything else. Plug it in the bottom one, cancel what you can, hit it with the derivative. That's good. No problem. I'll write a few steps in so you can, if you're stuck. So take the derivative. Please no quotient rule, just use the x to the negative 1. It's times a constant. Do you all have a cube root of 100? Right, so this is roughly 4.6. Then we're going to take that and calculate y. So y is 100 divided by 4.6 squared. And we have about 4.7 on this one. So the box is 4.6 by 4.6 by 4.7 meters. This is more than twice my height, right? It's about 1 meter is about 3 feet, so it's a very large container. Let's see what other cool things we can compute. Oh, that's cool. We'll come back to that. So there was the box. Ooh, okay, that's a good one. So we'll do some business. All right, let's talk about this problem. In problem 29, with a flower garden, because I know you're all interested in that. Some of you more than others. So flower garden, the FG, that's in the middle, and we have grass all around. Is it grass or a concrete slab? Whatever. So this length over here is 2 meters, and this length over here is 1 meter. Again, 1 meter is about 3 feet, so it's 3 feet and 6 feet on sides. So let's say that's where the grass is, and then you have the flower bed in the middle. What do we want? A rectangular flower garden with an area of 30 meters squared. So flower garden inside is 30 meters squared, we know that. Is surrounded by a grass border 1 meter wide on 2 sides and 2 meters wide on the other 2 sides. What dimensions of the garden minimize the combined area? Minimize the combined area. Good. Dimensions. So dimensions that minimize the combined area. Wow. This is a cool problem. We'll see. We can calculate exactly what we need to do. So after this, we're going to take a break, and then we'll have another 2 problems and a challenge. So, let's label things first. I'm labeling the inner side x and the inner side y. And if I label inner side x and a y, then what are the measures of the outside sides? X plus 4, very good, and y plus 2, nice. So as soon as you put x and y on the inside, then you're adding 2 meters on each side to this x. So 2 plus x plus 2 is x plus 4. And then y is y plus 1, so y plus 2 for the outside. We know that we want the outside to be minimum, so, and that's area. So x plus 4. That 4 is weird. So x plus 4 times y plus 2 is minimum. That is our objective equation. And then for the inside of the constraint, they say the area of the inside is 30 meters squared. So how do I write that? Yes, it's area, xy. xy equals 30. Good. So, solve for either x or y. Okay, y is equal to 30 over x. And then plug in. So what do we get? We get x plus 4. And instead of y, we get 30 over x plus 2 to be minimum. Foil this. That's x times 30 over x, that's just 30, plus 120 over x, plus 2x, plus 8, equals a minimum. So we have 2x plus 120 over x, plus 38 equals a minimum. Differentiate in respect to x, so you can minimize. 2 minus 120 over x squared plus 0 equals 0. 120 over x squared equals to 2. And finally, x squared equals to 60. X is equal to plus minus square root of 60, but the lengths can't be negative, so drop negative. And the square root of 60, well, it's 2 root 15, but we want to have some decimal approximations, is about 7.7. Drop negative. It's a length. Every time you are wondering if the lengths could be negative, well, just think that you are always a positive amount of miles away from your house. And when you're home, everything else is again positive amount of miles away. So lengths are always positive, so we drop a negative there. So I have 7.7 on x. I can calculate y is 30 over that. So y is 30 divided by 7.7, right? Which is going to be about 3 something. $3.9, yeah. And they say what dimensions? Well, the outside dimensions. So we have to add 4 on x. So that's 11.7 by this plus 2, so 5.9 meters. Outside dimensions. Now it takes some ingenuity to figure out where else you can use this problem. Pool design, which is engineering fee, you get paid for that. If you take a look at the textbooks have margins. So you are going to have a page with the text inside and the margins on the outside, and then you know that you need certain amount of square inches for the text and the pictures and everything else that is content of the book. But then you also have to have margins around. And what do you want to minimize? Well, you want to minimize the size of the page, the less paper, the less cost to print, right? There's a reason why publishers are dying today. Because what is the cost per page for a digital format? 0, right? And your generation reads off of the screen rather than off the book. Newspapers, gone. Magazines, on their way out. Books, give another 5-10 years. Gone. All gone. Right? All of the companies are now trying to figure out how to move because, again, costs money. So now, to save money, you say, all right, I need an inch margin on the left-hand side so I can bind the book, right? And I need half an inch on other sides to, right? So those become your dimensions. We used to have, 1 and 2. Now they're 1 and 0.5, 0.5, 0.5. They go in these equations, and you figure out it's the same problem. I just figure out what is the application that actually makes money. So, figuring that out. All right, so this is a long lecture. Obviously, word problems are very important. So let's take a break, and after the break, we'll have part 2. A few more examples and challenge homework project, mini project. See you soon.